Scaling out from the Milky Way, the local group is defined by three major gravitationally bound galaxies: the Milky Way, Andromeda, and the Triangulum Galaxy. Triangulum, or M33, sits 2.73 million light-years from Earth and contains a total mass of roughly 40 billion stars. This diagram scales M33's apparent angular size of 70.8 by 41.7 arcminutes directly against a standard full moon. From Earth's perspective, the galaxy is over twice as wide. Despite being the third largest member of the local group, M33's star formation rate is 10 times higher than its larger neighbor, Andromeda. Its proximity and intense stellar activity make M33 a high-resolution laboratory for tracking galactic evolution in real time. M33 is classified morphologically as a pure disk galaxy. These galaxies lack a central, densely concentrated stellar bulge. There is also no kinematic evidence for a supermassive black hole at the galactic core. This structural type accounts for only 15 to 18% of galaxies in the observed universe. M33 maintains an intense star formation rate without a massive central bulge to drive density waves. Broadband imaging shows organized spiral arms, suggesting the galaxy has not suffered a major collision that would typically trigger such a starburst. Identifying the drivers of this stellar activity requires dissecting the galaxy by the specific ages of its stellar populations. The Patter survey resolves individual stellar populations within M33 across different wavelengths. When observing only young stars and gas, M33 displays a flocculent spiral classification, a patchy, disjointed, multi-armed structure. Isolating the oldest stellar populations, specifically red giant and asymptotic giant branch stars, reveals a classical central bar structure with a 350 parsec radius. This exposes a distinct underlying two-arm spiral with a strong M=1 mode asymmetry, normally masked by younger gas. This morphological dichotomy implies the visible gas is tracking a recent dynamic instability rather than the galaxy's true bulk mass distribution. A past tidal interaction with the Andromeda Galaxy likely disturbed the interstellar medium while leaving the old stellar mass intact. M33's flocculent appearance is a superficial layer of active star formation layered over an ancient galactic skeleton. Moving from the galactic scale down into an active spiral arm brings us to the starburst region NGC 604. NGC 604 is a giant H2 region spanning nearly 1,500 light-years. This interstellar cloud of ionized hydrogen acts as an incubator for over 200 extremely hot, massive stars. Dynamics here are driven by O-type and B-type stars, some exceeding 100 times the mass of the Sun. Extreme stellar winds from these stars generate physical shocks that carve cavities in the molecular dust. Intense ultraviolet radiation strips electrons from the surrounding hydrogen, causing the cavernous gas walls to fluoresce. These massive stars actively dismantle and reshape their surrounding interstellar medium. Mapping the chemical layers of NGC 604 requires looking beyond visible light. The James Webb Space Telescope uses its near-infrared camera and mid-infrared instrument to pierce the nebula's dust. NARCam data identifies polycyclic aromatic hydrocarbons, or PAHs, which appear as bright orange streaks inside the nebula. These complex carbon-based molecules seed the interstellar medium for the formation of future stars and planets. While infrared penetrates dust, optical spectroscopy, using instruments like SETEL, maps the gas kinematics. Integral field spectroscopy, or IFS, captures spatial location and precise spectral emission lines simultaneously across a wide field of view. Mapping emission lines like H-alpha and ionized oxygen calculates exact gas conditions like electron temperature and density. This produces high-resolution metallicity maps, tracking chemical abundance variations across a fine 3-parsec scale. IFS data also reveals localized kinetic shocks and gas turbulence driven by supernovae and stellar winds. Combining infrared penetration with IFS maps creates a quantifiable dataset for chemical and kinetic evolution. Scaling back to the macro scale of the local group reveals the three galaxies as a single gravitationally bound system. M33's hot inner halo and high star formation rate are symptoms of a dynamic gravitational interaction with Andromeda and the Milky Way. These kinematics are measured by tracking the lateral motion of the Andromeda Galaxy's halo across space. Data indicates a direct collision between the Milky Way and Andromeda in approximately 4 billion years. During the initial merger phase, tidal forces will stretch and distort the thin spiral disks as the galaxies pass through one another. The encounter will compress the interstellar gas of both galaxies, triggering starbursts across the entire sky. 6 to 8 billion years in the future, the Milky Way and Andromeda cores merge. The result is a single, massive elliptical galaxy, devoid of spiral arms or a central disk. Starbursts from the merger will have scoured the combined system of cold dust and gas. Without gas, star formation ceases, leaving an aging red stellar population. This vector simulation tracks the projected orbital trajectory of M33. Current models show it either entering a permanent halo orbit around this new elliptical system or being consumed by it. By resolving the microscopic physics of H2 regions and the stellar architecture of M33 today, we are observing the kinetic blueprint of our own galaxy's ultimate destiny.